This same analysis can be done and is done in the chapter using stochastic processes, in particular geometric Brownian motion. And the reason that all of the math will work exactly the same way, and it's detailed in the chapter, is because this is just a continuous time model for the returns we saw a moment ago. So let's actually investigate. But here we have, imagine, two geometric Brownian motions, and they are perfectly correlated, and you can tell that because they have the same dz. One of the things you have to be careful about when you're dealing with stochastic processes is if you write dz in two different equations, it is always assumed that they are the same dz. In other words, the dz factor for one process will be the same as the dz for the other. And it's important that if you want the dz values to be different, they might be independent or correlated, you have to use different notation. So when we write this expression, this terminology, this notation means that we're using exactly the same Brownian motion to drive each one of these stock prices. That's what makes them perfectly correlated. And we can now make the same observation, namely that because these two geometric Brownian motions are perfectly correlated, they must have the same Sharpe ratio. And notice that the definition of Sharpe ratio for geometric Brownian motion looks just like it does for an ordinary stock, because alpha 1, the coefficient of the drift term, is the instantaneous return, and sigma 1 is the vol. So the notation is suggestive, and by simply taking the parameters from those two equations, we must have this same calculation. And the derivation is identical to the one previously, and that is that if we, again, went long 1 over sigma 1 S1 shares of S1, short, same formula. So we use exactly the same setup. What we would get is we would get that the change, if I is the portfolio, we would get that the change in I is equal to DS1 over sigma 1 S1 minus DS2 over sigma 2 S2, and then we have this cash position 1 over sigma 2 minus 1 over sigma 1 R dt. So DS1 is so the change in our portfolio value reflects the change in stock 1, and I have 1 over sigma 1 S1 shares. I'm shorting stock 2, so I'm short the change in stock 2 scaled by the number of shares I have. And then I have a T-bill position which must earn R dt. T-bill position is going to earn R dt. And if I simply insert the formulas for DS1, DS2, you will notice, just as happened in the case of normal variables, normal returns, that the dz terms cancel out because they're a common factor. And we end up with simply alpha 1 minus R over sigma 1, and then minus alpha 2 minus R over sigma 2 dt. In other words, we have a portfolio I which costs nothing, and because the stocks are perfectly correlated, the change in that portfolio value is equal to this. Well, the only way I can avoid an arbitrage is I must have DI 0. If I have a portfolio in an economy that does not allow arbitrage, if the portfolio cost me nothing, then it must be the case that its change in value is nothing. Otherwise, or it's okay if it has a probability distribution of changes, some of which are positive, some of which are negative. But here we can see I have a non-risky return. DI is deterministic. It only has a drift term. So there cannot be an offsetting distribution of positive and negative returns. Since this costs me nothing, the only way I can avoid arbitrage is that this change is 0, this deterministic change. And then therefore I get that they're equal. So it's exactly the same derivation, no different.